Can you see my screen? I wait. Share screen. Can you see my screen, class? Linear differential equations.
Yes, miss.
Okay, thank you. So you have actually listened to the discussion on this already. So I will just go through it again. That way, if you have questions, you may ask me. So as you can see here, let me annotate. It is a requirement in terms of the form that your linear first order DE should have on its left side of the equation. This is the left side of the equation, the derivative of the unknown function. Then added to it is the product of your unknown function and an expression in terms of the independent variable. So this is your independent variable x, and this is your unknown function y. So it's a requirement that the left side of your DE, left side of your differential equation should look like this if it has to be linear. The right side should only contain an expression in terms of the independent variable. So this could be just one term, or this could be several terms, as long as it's just in terms of x. In this case, x is our independent variable. Let me check. Somebody wrote on the chat box. Okay, so that's for the attendance. Okay, now there are actually only two very specific procedures that you will perform, but in here it's written in three different separate procedures. The first thing you have to do, so this is, by the way, the third requirement in terms of the form of your linear first order differential equations. Okay, you need to find the integrating factor. In majority of the books in differential equations, it's represented as the phi, and its formula is e raised to the integral of p of x dx. This p of x here is the p of x here that is multiplied to your unknown function on the left side of your differential equation. Of course, the second part would be the evaluation of this integral. So you evaluate, or you find the value of the phi, given that it's e raised to the integral of by the way, class, this is not q of x. This is p of x. Okay, given this one, you need to evaluate the phi. Now, after that, you find the solution already of your linear differential equation. The solution is very straightforward. The left side constitutes the product of your unknown function, whatever is your unknown function, and the phi that you got after you have evaluated already this one. So the left side is the product of the two, and the right side would be the q of x that you have here on the right side, multiplied by the phi. Then the product of these two is integrated, or the integral of the product of these two is evaluated. And this is how you determine the solution of your linear first order differential equation. Actually, there's just two procedures. Find the integrating factor and then use this formula to determine the solution of your linear first order DE. Okay, now let me clear what the markings here. So far, do you have any question as to the form of a linear first order DE? Okay, I gather there's none, so we'll proceed to the example. Here on the example, normally when I give an example, I don't give an example that looks linear right away, or I don't give an example that looks, shall I say, Bernoulli or separable in terms of the form, because these types of DE are only requiring that they follow a certain form in the manner the equation is written. The other two that we have discussed, the homogeneous differential equations and the exact differential equations, both require that you do some testing. So for these three, there's no testing. All you have to do is check the form. So in this particular DE, you can see it doesn't look linear, but you can make it linear by, of course, you transfer the first two rather you transfer this term here on the right side because it doesn't contain any unknown function. So you transfer it on the right and you isolate the derivative that you have in here. Isolating meaning you eliminate the multiplier x on your derivative. So how will you accomplish that? So you can accomplish that by dividing your entire differential equation here by x. So which means that you eliminate x here, you introduce x in the y here. The same thing with the 4 in here. So y becomes y over x and 4 becomes 4 over x. If transferred on the right side, it becomes negative 4 over x. Now, if your DE is written in this form already, it looks linear. Okay, this is your derivative. Your P of x is the 1 over x, the part wherein the other part, if you take away the y in the picture, because your y is your unknown function, so the multiplier to it is your P of x. In this case, it's 1 over x. Your Q of x is the rest of the expression on the right side, which is solely a function of x. Okay? So if you have written your DE already in linear form, the determination of the P of x and Q of x is very simple because you could see it right away in the form. What are these two? When you already know your P of x, you make it as the argument of the exponential function, this one, and integrate such expression. In this case, it would be e raised to the integral of 1 over x dx, which will give us an e raised to ln of x. And based on what was discussed in your differential calculus, e raised to an ln is equivalent to 1, leaving you with an x here. So then, you know already your integrating factor. Since you know already your integrating factor, you just go back to the formula for the solution of a linear first order DE. The unknown function is multiplied to the integrating factor, the phi. So that would be in this case, xy or yx. And then this part here is actually the integral of your q of x is negative. So I'll place negative here, 4 over x. And then you're going to multiply it with the phi, which is x, dx. In the process, you eliminate the x, leaving you with a negative 4, which when integrated would give you negative 4x. If you transfer it on the left side, it looks like this. It becomes plus 4x. And don't forget the arbitrary constant c that should be written on the right side of your linear DE. So this one now is the solution of this linear DE that was provided to you. So, but first, of course, you notice that it doesn't look linear. You have to make it look linear first before you use the procedure in finding the solution for a linear DE. Now, class, if the DE is not linear and you're going to solve it using the procedure here for linear DE, your solution will be wrong. So it has to conform to the form of a linear DE first before you're going to use this set of procedure. Actually, there's only 3. Okay? Now, do you have any question? Questions? Okay, so I will clear now and there's none. Actually, I only placed one example for each because I want you also to practice on your own. Anyway, they're very simple. Now, let me give you another example on, I will stop sharing and we'll use the Jamboard. Wait, class, huh? We'll use this one. That way, I can give you added example. So let me share this one. So let's have another example for a linear first order DE. Okay, so this would be your example number 2 for linear first order DE. We'll find one in here. Okay, let's use something that is not linear the way it looks. So 1, plus cosine of x, and this is multiplied to y prime, and you'll have here a sine x times sine x plus sine x cosine x minus y. Okay, now the differential equation doesn't look linear. Okay, who would even think that it's linear? So if this is probably given to you, you will try to check whether, of course, you have to start with the simplest. You have to check whether this is a parabol. Then you check for homogeneity. Upon inspection, this is never homogeneous. Then you will check for exactness. I don't think this will be exact. So the next thing that you will do, check whether the form could be rendered linear, or it will conform to the linear first order differential equation form. Now, the first thing that you will do in this case to check whether this will conform to that of the first order linear, you will get rid of this in here by division. So you divide your entire differential equation by the quantity 1 plus cosine x, because you want your derivative to stand alone, meaning its coefficient should be only 1. So we will do that. So we will divide this differential equation by 1 plus the cosine of x. In the process, that way we will not incur so many lines in our solution. I will write the remaining y prime on the left side. Then I will have this expanded. Okay, I will have this expanded. But before I do expansion, check first that there is something common between the first and the second terms in here. So you see a sine x and a sine x in here. So what I'll do is this. I'll take out what is common and check whether I will have an expression comparable to this when I do division already. At first class, you didn't know that it will happen. You will just go, you will just know as you go along with your solution. So I will place here my division, my line for my division. Then I will write here sine x. Then as I have said, I will factor out the sine x in here. So if I will do that, for my first term, I will have a 1. For my second term, I will have the cosine of x. Okay? Remember that you only factored sine of x for the first two terms. The last term does not have it, so it's still y. Okay, so this multiplied to this is just the same as the original expression. And I will have the cosine of, or rather 1 plus the cosine of x as my divisor. Now, if you will distribute the expression 1 plus cosine of x to these two, you will see that upon distribution of the sine of x multiplier in here and in here, this will be your corresponding expression. So I'm fond of merging my processes class. That way I will not have a very lengthy solution. But if you think you will be better off with first doing the expansion and then division, then do so. In my case, I do it because I want to save some lines and I want to save time in writing a lot of lines in my solution. So if I will now use this as a divisor for my first term and my second term, what is left for this one is, excuse me class, there's something wrong with my board. What is now left here is just the sine squared of x. Sine x and the sine x, because this one is taken out of the picture. Then this one will be multiplied now to sine x and 1 plus cosine x. So I will have to write minus, because it's minus here. Then I will have the sine of x over 1 plus cosine of x. Then this is multiplied to y. Okay? Now, this doesn't look linear, but when I rewrite again, so I will have my derivative here. I like to transfer this on the left side. So it is negative here. So that would be positive here now. So it is sine of x over 1 plus the cosine of x times y. And what is left on the right side is just the sine squared of x. If you look very closely, the original given dE, which is not linear, is now linear. This is my derivative y prime. This is my p of x. Of course, this is my y. And this is my q of x. Now it is made linear. When it is made linear, then you can proceed with determining the integrating factor. So the integrating factor will be needing your p of x. Okay? So any questions so far here? Okay, so I will here my markings. Now, if we will proceed to the next slide, it's okay not to clear my markings. Your phi is equal to e raised to the integral of p of x dx. It's equal to e raised to the integral. So on the previous page, you see that your p of x is this one, sine of x, 1 plus cosine of x. So I'll place here sine of x over 1 plus the cosine of x dx. So the rest would be your calculus in terms of evaluating this given integral. Now, if you set the 1 plus cosine of x as your u, if this is your u, the numerator du will be negative or should be negative. And since our original integral does not have a negative sign here, then I'll place a negative sign outside. That way I did not alter at all my original integral. The purpose is I can simply have the integral of sine x over 1 plus cosine of x. Okay? So if you have a du over u, the integral will be ln, the ln of u, whatever that u is. In this case, that would be e raised to the ln of u, which is 1 plus the cosine of x. Now, this negative 1, this is to be understood as negative 1, is actually the exponent of the argument of your ln here. So you can write your exponential function here as e raised to the ln of 1 plus the cosine of x raised to negative 1. The purpose of this is for you to be able to simplify this expression, knowing that e raised to ln is 1. So what you'll have here now for your phi is 1 plus the cosine of x raised to negative 1. Or shall we say your phi, if it's negative 1, then it would be 1 over 1 plus the cosine of x. So this is your phi now. Once you have the phi, the rest is substitution to the formula of the solution of your linear first order differential equations. So that formula is y times phi times the integral of q of x dx. Okay, what's wrong with, okay? And then you substitute. So your unknown function is y. Your phi is 1 over 1 plus cosine of x. And your q of x. So what is your q of x? So your q of x is sine squared of x. As you could see here, it's sine squared of x. So we go to the next page and place here sine squared of x. That's your q of x. By the way, I'm miswriting here the phi. Okay, the product of q of x and the phi is the integral that should be evaluated on the right side of the solution of your linear dE. So we need to multiply this by 1 over 1 plus cosine of x. Okay? So actually, the rest is your calculus because you cannot finish the solution of this DE unless you know your calculus. You can evaluate this particular integral after you have written or you have converted sine of x to its equivalent identity. So the equivalent identity of sine squared of x is 1 minus cosine squared of x. So if you will substitute that in your integral, so it would be 1 minus cosine squared of x over 1 plus cosine of x dx. Again, in here, you will use another identity. That way you can simplify your integral before you evaluate. The identity equivalent of this that will help you simplify the given integral is from your trigonometry, 1 minus cosine x and 1 plus cosine of x. Okay? If you multiply these two, the answer is this one. So in the process, you get to cancel the 1 plus cosine of x here in the denominator and this one, leaving you with an integral which is 1 minus cosine of x dx, which is actually x minus sine of x, of course, plus c. The integral of the cosine is the positive sign, so you carry the negative sign in here. If you want to explicitly write the solution for this, for the given differential equation, you can cross multiply 1 plus cosine of x in here. So you will have y equal to, so you will have 1 plus the cosine of x times x minus the sine of x plus c. Now, this is the explicit solution to your given first order linear differential equations. Do you have any questions? Is everything clear? Okay, no questions in the chat box. You are silent, so I'm hoping that you follow through. You can follow through. Now, there's no question here, then I will share to you the second slide, which is about Bernoulli's equation. Okay. Wait, class. Okay, we'll share. Oh, different one. Wait. Share. I think it's this one. No, this one. Okay. So we have now, I hope you can see, it's Bernoulli's equation. The reason why I discussed these two simultaneously and even pre-COVID time, I discussed this in just 1 hour. I can finish more than in just 20 minutes, probably, the concept of the two, because in terms of the form class, they're really very similar. So when we speak of Bernoulli's equation, in terms of the form, it looks very similar to that of your linear first order differential equation. So same on the left side. So the thing that differentiates the two is what is written on the right side. You could see this one, the y raised to n. Your n here should not be equal to 0 or 1. Okay? So if it's 0, if your y is raised to n, rather if your n here in your y is equal to 0, that's equivalent to 1. And this is not anymore a Bernoulli equation. It's now what we call as a linear first order DE if your y is raised to 0. Now, if your y is raised to 1, you have a y here and you have a y here, the given differential equation is already separable because you need only to transfer the p of xy on the right side. then factor out the y, then you can already separate expressions of x and y. And you can group them together with the differentials y and x also. And that will help you evaluate your differential equation. So the only difference of the linear and the Bernoulli's equation is this y raised to n that is being multiplied to the q of x expression on the right side of your dE. Now, in terms of the formula, also very similar. There's only an added thing here for Bernoulli's equation. So you could see that in the integrating factor, you have already 1 minus n as a constant that is being multiplied to the integral of p of x dx in your exponential expression to be evaluated. Okay? As to the formula, so this is the first step, you determine the integrating factor. The second step is just plug in the phi and the rest of the expressions that are needed in this formula for the solution of your Bernoulli's equation. So again, in your linear dE, you don't have this. You simply have y. And on the right side, you don't also have 1 minus n. But in Bernoulli's equation, you have it. So the only difference in terms of the solution of the two equations is the presence of the 1 minus n constant. Okay, for the integrating factor and for the solution of a Bernoulli equation or of a Bernoulli's equation. Okay, now let me clear my markings. Now, if you go to the example that is given here, now, again, I chose an example here that does not look Bernoulli. It doesn't look like a Bernoulli's equation, but it can be rendered as Bernoulli's equation. So first thing is, since you don't have the presence of the derivative, you choose the derivative, the appropriate derivative for this dE. Now, if you're going to ask, is there a particular, shall I say, thing in terms of the form of the dE that tells you that it's Bernoulli? My answer is no. You only get to know that it's Bernoulli after you have tested that the other methods will not work for it, or it doesn't fall on any particular type other than this one. So if you check this one as separable, you can do that. It's not separable. If you check if this is homogeneous by inspection, this is never homogeneous. If you test whether this is exact, this is never exact. So this is how you should do it. You check it piece by piece, and if one particular form will not be suitable for a given dE, then you go to the next. Then, of course, you will have now to check whether this is linear or Bernoulli. For now, if you're the one processing this, you don't know that this is Bernoulli, but later on, it will just simply be, you will simply discover as you go along that, this is really Bernoulli. So as I've said, you first determine the derivative. So you divided. So in this case, let me annotate. You will divide your original dE by dx. So if you divide by dx, I'll just place it here. You will eliminate the dx in this part, and you will introduce the dx on the dy. So this becomes dy dx. Now, it's a requirement for both linear and Bernoulli's equation class that your derivative should not have any multiplier on it or coefficient on it except 1. So in this case, there's also a need for you to eliminate the 2x. So for you to be able to eliminate the 2x is for you to divide also by 2x. So in the process, in this term, you will eliminate the 2x, but you will be introducing the 2x on this side. That's the very reason that you have this dE in here. You have now dy dx. You have now the dy dx in here. 2x was already taken out, and this one. So why you have 6y cubed minus xy minus y? It's because you did expansion in here. So that would be this one, and then you divide it by 2x. There's nothing written on the right side, so 0 divided by this 2 would still be a 0. The next thing that you do is you look very closely on this rational expression that you have. Now, remember that you know already that this is not separable, exact, or homogeneous. So you have only in mind that whether this could be linear, rendered linear, or Bernoulli. Now you could already see that your y has an exponent here other than 1. So it could never be linear because for linear, your y should be all raised to 1. So even if you're going to factor out the y in here, you still have a y squared remaining. So in that case, now that tells you this could be Bernoulli because this one, this expression here could be a part of my q of x y raised to n expression, which should appear on the right side of my dE. And true enough, class, if you simplify this here before you will have this one, in here, this is negative. So I will have negative, I will factor out negative y, so I have negative. So I will have an x plus, if I'll take out negative y here, that would be 1. And that should be y. And this one is plus 6y cubed. Okay? Then I will divide by 2x. So, by the way, so I will need to erase this one. Wait. So this is actually this part. So I should not place there an equal sign. This is only the first part, this one. So if this negative thing here, which has the y, I'll use a different color so you will see clearly. If this y is isolated, oh, cannot use this one. You will have this one. Here. Negative quantity x plus 1, 2x. As your, this time, this is your p of x. This is your y. And in here, if you're going to distribute the 2x as a divisor to these two terms here, the second term will yield a 3. You get to cancel the 2, and you will be left with the 3 here. Now, since this is here on the right side, left side rather, and you're going to transfer it on the right side, it's now negative. So you have negative 3 over x. This is now your q of x. And you have y cubed. So in here, for original, not so Bernoulli's equation, dE, was now rendered, or in terms of the form, was now, looks like now a Bernoulli's equation. So your p of x is negative x plus 1 over 2x. I would like to emphasize the negative because if you wrote positive, your answer would be totally wrong because we are very, very careful with the signs of the p of x and the q of x, especially when we're dealing with this particular type of dE. Same thing with linear, because in the evaluation of the integrating factor, the sign plays a very important role. Your q of x is negative 3 over x, and your n, in this case, is 3. Your n is 3, okay? So in terms of finding your integrating factor, it's e raised to 1 minus n. That would be 1 minus 3. So you get here a negative 2. And you have the integral of, so this is your p of x. And notice the negative here. Negative quantity x plus 1 over 2x dx. So what's done in here is to, so we'll simplify. So this is negative 2, and you have the integral of, in this case, if you distribute the 2x as a divisor for x plus 1, that would be negative 1 over 2. And for the second term, that would be negative 1 over 2x. This is dx. Okay, both has 2 in the denominator and both are negative, so we can now cancel this one, the negative and the 2's, leaving us with the what? So you will have an e raised to the integral of, I already took out the negative because it's negative, integral of 1 plus 1 over x dx. What's the integral of this? So that would be e raised to x plus ln of x. See this one? This If this is evaluated, this is x, and this one is ln of x. Now, rules of exponents dictate that if you have exponents being added with a base, which is e, it's like the same as e with these two exponents here. Now, two e's that are being multiplied. So the exponent of the one is x, and the second one is ln of x. Now, this one again will be equal to 1. So you have x e raised to x. So this is now your phi for this Bernoulli's equation. So this is your Bernoulli's equation. Actually, this one is also Bernoulli's equation, only that in terms of the form, you will never think that it's Bernoulli's equation. Okay? Now, before I go to the next slide, do you have any question here? Okay, so I will clear all the markings. So if you have that already, so you go to the formula. So y raised to 1 minus n times the phi. This is your phi. Your 1 minus n is negative 2. Your q of x is negative 3 over x. And this is your phi again, which will cancel out the x's. Okay. So you have a negative 3 and a negative 2. That would be a 6 e raised to x dx. So this is your integral already. The left side would simply be now x e raised to x if this y raised to negative 2 is transferred here on the other side through cross multiplication. Now, any questions so far? Okay, no question? Sige, so if there are no questions here, let me check the chat. Okay, no question on the chat box either. So we'll have another example of a Bernoulli equation or Bernoulli's equation. So you see, this is actually the end for this one. So we'll go to our board and let me stop sharing. Okay, we'll go to our board and have another example for Bernoulli's equation. Let me share. Okay. So this we will now start with a clean slate. Okay, we'll have a Bernoulli equation, or we'll have Bernoulli's equation. Okay, we'll choose another one which doesn't look like Bernoulli. Okay. So we check. Okay, this would be our second sample problem. We have 2x cubed y prime equal to y times y squared plus 3x squared. It doesn't look Bernoulli, but we can check whether this can be made Bernoulli. So there's no specific first step or second step here. You can do expansion first, or you can isolate the y prime in here. It depends on you, but as long as you make sure that your DE is first Bernoulli's equation in form before you solve it using the Bernoulli's equation technique. Okay, so what we're going to do is we'll do expansion. So you can have this expanded. So in the process of expansion, you will have here y cubed plus 3x squared y. Okay. Then I'd like to isolate the y prime here, so I can divide by 2x cubed. If you do that, you will have y prime left on the left side, and you will have, I'd like to distribute the 2x cubed to this 2 here as a divisor. So I will have 3x squared over 2x cubed, then I will have y. Then on the other one, plus 1 over 2x cubed times y cubed. So the way I'm writing it is already forthcoming of what's the next step that I will do. I intend to make it look Bernoulli, so that is why I isolated already the y that is raised to a higher exponent. The y that is raised to 1, I also isolated in here on the first term. I can cancel this out. That leaves me with 1x here in the denominator. And I can transfer this one on the left. So I will have y prime, by the way, wait, equal sign. So you have y prime minus 3 over 2x times y being equal to 1 over 2x cubed times y cubed. Now in here, you can see already that your original DE that doesn't looks like a Bernoulli's equation is a Bernoulli equation. So this is your P of X, and this is your Q of X, and this is your N. So your N is equal to 3. So knowing that these 3, very important, P of X, Q of X, and N, you can now go to determining the integrating factor. So your phi is equal to e raised to 1 minus 3 integral of, so our P of X is negative 3 over 2x. So I have here negative 3 over 2x dx. Now in the process, this one is negative 2. So this can cancel with the 2 in here, leaving me with a 3 dx over x. So the integral of such is very simple. So you have a e raised to, so you have a 3 ln of x. So you take away the negative 2, and that leaves you with a 3 over x dx. So that's 3 ln of x. This 3 actually is the exponent of the x here in the argument of your ln, and this is x cubed because this one is 1. And that's it. The solution of your Bernoulli's equation would be then y raised to 1 minus n times this phi equated to 1 minus n integral of, so what is our q of x? So our q of x is 1 over 2x cubed. So I will have here 1 over 2x cubed for my q of x. Then it should be multiplied to my phi, which is x cubed dx. Let me check if our q of x is positive. Okay, this one is positive. Okay, then you could see that we can cancel the x cubed. You can cancel the x cubed here. And this one is negative 2. So this cancels with it, leaving you with a negative integral. So your right side now will be negative. So nothing here. So negative x. Let's see. Now this one is y raised to negative 2, or that's equivalent to x cubed over y squared here on the left side. So if you want to write your solution in a manner in which you don't have a denominator, nor do you have a variable raised to a negative exponent, This y raised to negative 2 should be written as x cubed over y squared and cross multiply the y squared. So your solution for this DE would be y squared times c minus x. So I wrote c first because it's positive, but it's okay if you write negative x plus c. Now this is the solution of your Bernoulli's equation. So the solution is very short actually. The part which took the part of the solution which took time is this one. It's always part of the solution. Rendering your given differential equation linear or Bernoulli's equation in form prior to using the procedure of finding its solution, because you cannot use the said procedure unless you know the p of x, the q of x, and the n in the case of the Bernoulli's equation. In the case of the linear DE, that would simply be p of x and q of x. Okay? So 2 minutes before time, do you have any questions? No more questions? I'll stop sharing. I'll check the attendance on the chat box. Okay. So no more questions, class. So Wednesday, I'll post a recording for the last two topics. The inexact DE made exact and differential equations solved using the method of substitution. And on Monday, prepare for a quiz for this four. Anyway, I'll give you additional solved problems on this four that you can study. But nonetheless, I would like you still to practice solving your problem set, finish it, and then submit it on the due date that I will place in Canvas, that I will specify in Canvas. And I think that would make you ready to take the quiz afterwards. Okay, always practice solving, that way you would know what particular method or technique will you use, or what particular form of first order differential equation is given to you. So there's no clear-cut procedure in how you're going to tell which is which or what you will do. You will just simply learn as you practice. Okay? No more questions? Okay, if there's none, so that's it for today, class. Bye. I'll see you next week, Monday. Should you have any questions, let me know. Drop me a line in my messenger or even in Canvas through inbox. Okay? Bye for now.
Thank you, Miss.
Okay, okay.
Bye, Miss. Thank you.
Okay, thank you also.